Hello, discrete math fans. We've got a few special graphs that we want to talk about. They'll come up often, so they're worth knowing about. First of all, there's a simple graph. A simple graph doesn't have any loops or parallel edges. Then there is the complete graph on n vertices, which will denote Kn. It's a simple graph with n vertices and exactly one edge connecting each pair of distinct vertices. Here are the first few complete graphs. K1 has no edges because there's no other vertices to connect to. K2 has only the one edge because there's only one way to make a connection. And as the number of vertices gets larger, the graph gets more interesting looking. Here's K5 that has 5 vertices and an edge that connects every possible pair of vertices. Remember, there are no loops and no parallel edges because these are simple graphs. Next type of graph we want to talk about is one in which the vertices can be partitioned into two sets, V1 and V2. And let's assume that the only edges in the entire graph connect a vertex in V1 to a vertex in V2, so that there are no edge connections between vertices just in V1 or just in V2. This is called a bipartite graph. And then there is the concept of a complete bipartite graph. That has edges between every vertex in V1 and every vertex in V2. Here is a formal definition of a complete bipartite graph. We will denote such a graph with KMN. It is a simple graph. It has distinct vertices V1 through Vm and W1 through Wn that satisfies these three properties. For all I and k in the set 1 through m, and for all j and l in the set 1 through n, we get that there is an edge from each vertex vi to each vertex wj, and then there is no edge from any vertex vi to any other vertex vk, and there's also no edge from any vertex wj to any other vertex wl. We'll see this with some pictures in just a moment. Here are some complete bipartite graphs, and you can see this is K42 because there's 4 vertices on one side, 2 on the other, and then here's K33, 3 vertices on one side, 3 on the other. We have an edge between every possible pair of vertices in the two sets. And the last thing we want to talk about is subgraphs. If we start with a graph G, then a subgraph H of G is a graph where every vertex in H is a vertex in G, and every edge in H is also an edge in G. Okay, we can think of subgraphs in the same way that we're going to think of subsets. So later on in the class, we will talk about sets and subsets. So we start with a graph, we delete vertices and edges, now we have a subgraph. If we delete a vertex, then we must delete any edges adjacent to that vertex. Okay, that's all for now.